The Einstein field equations of general relativity offer various solutions, each describing different forms of curved spacetime. Modern black holes were initially discovered by Carl Schwarzschild through these equations. However, at that time, this was merely a mathematical solution, and nobody believed it had any physical relevance. It was J. Robert Oppenheimer, known as the father of the atomic bomb, who grounded the concept of black holes in reality. He further developed the neutron star model to predict the possibility of actual black holes, although they weren't called black holes at that time. In 2019, scientists unveiled the first ever photograph of a black hole, putting to rest any controversy about their existence. But what about the concept of white holes, also stemming from Einstein's equations? These remain an unconfirmed prediction. If they do exist in the universe, what would they look like? Many of you might have some idea about white holes. Unlike black holes, which constantly devour matter, white holes continuously expel matter. The event horizon of a white hole isn't a boundary you can't escape. Rather, it's a region that nothing can enter. Here, spacetime curvature is also infinite, but it's negative, implying an infinitely strong repulsive force acting on external matter. Hence, once something emerges from a white hole, it can never return, not even light. In terms of timelines, its entire future is outside the white hole. The concept of white holes was first introduced in 1964 by Soviet theoretical astrophysicist and cosmologist Igor Novikov, through further calculations based on the Schwarzschild solution. Like the Schwarzschild black hole, the white hole was initially just a mathematical construct. So what about its physical meaning? While black holes form from collapsing massive stars, according to Oppenheimer, the formation and existence of white holes remain difficult to understand. Moreover, some have proven that white holes inherently cannot exist stably. We cannot observe a persistently existing white hole. Shouldn't white holes, constantly ejecting matter, be easier to observe than black holes? Black holes are black because nothing escapes their gravitational pull, rendering them unobservable. We usually locate them through their gravitational effects or the radiation from their surrounding accretion disks. In contrast, white holes are continuously ejecting matter. So why can't we observe them? The reason is simple. The matter they expel quickly forms a black hole due to gravitational forces, making them indistinguishable from black holes in practice. Structurally, white holes and black holes are quite similar, each having a boundary akin to an event horizon. Both are strong sources of gravity, affecting external matter and possibly forming accretion disks. The difference lies in their interactions with these disks. Black holes pull matter in, while white holes cause incoming matter to collide with their ejected matter, creating accretion disks with radiation far more powerful than those around black holes. Some anomalous gamma-ray bursts, GRBs, have even been suggested to be modeled using white holes. Indeed, gamma-ray bursts are among the phenomena in the universe that currently most resemble white holes. Gamma-ray bursts are considered the most energetic explosions in the universe, second only to the Big Bang. Various models have been proposed to explain them. For instance, long gamma-ray bursts lasting more than 2 seconds are thought to be related to supernova explosions. Short bursts, lasting less than 2 seconds, are believed to result from collisions between neutron stars or the merging of a black hole and a neutron star. However, some gamma-ray bursts are puzzling, like GRB 060614 discovered in 2006. Although it exhibited the characteristics of a long burst, lasting 102 seconds, there were no signs of a supernova at its location. Some astronomers speculate that there may be an undiscovered type of hybrid burst, and others suggest that white hole models could explain it. The white hole explanation for gamma-ray bursts is particularly fitting for high redshift scenarios. This is because collisions between massive objects like neutron stars usually happen in regions densely populated with stars. High redshift indicates early universe conditions where such collisions would be rare. Therefore, using white holes as an explanation may be more plausible than stellar collisions in these cases. Apart from gamma-ray bursts, the concept of white holes was once used to explain quasars and active galactic nuclei, although this idea has since been abandoned. Quasars are now understood to be a type of active galactic nucleus, essentially supermassive black holes with accretion disks. The only event in the universe that completely aligns with the white hole model might be the initial Big Bang, which can be seen as a brief, erupting white hole. Note that the white hole in the Big Bang is not ongoing. It refers to the initial moments or instant of the Big Bang. After that, the universe's expansion is purely the expansion of space itself, not an erupting white hole. If the original Big Bang was a gigantic white hole, any existing white holes in the universe could be termed mini-Big Bangs. Both share similarities, like sudden and random appearances, making them impossible to predict. Prior to their emergence, white holes exert no gravitational effects and thus have no definite coordinates in spacetime. In summary, like the Schwarzschild solution that originally predicted black holes, white holes remain a mathematical solution in general relativity. While their external gravitational properties are identical to black holes, their internal properties are the temporal inverse. While black holes have a future singularity, where matter ends up and time ceases, white holes have a past singularity, where particles and their timelines originate. As for where these singularities come from, the answer is, we don't know. Both white and black holes present singularities that current physics can't describe. Particles emanating from a white hole never return once they pass through its event horizon. Physically speaking, white holes are unstable. Their emergence would necessarily be accompanied by the creation of black holes and their own decay, making it impossible for them to form stable celestial bodies. Thus, even if white holes exist in the universe, capturing one would be challenging. One reason we haven't observed them may not just be that they don't exist, but also that our observational window is too short. There's a saying, white holes act as the exit for what black holes consume. Connecting the two could be a wormhole, a concept often featured in science fiction as a bridge that traverses spacetime. So, is there any basis for the idea that wormholes link black and white holes? Stay tuned for our next discussion.